Transfer systems are electromechanical devices used when there is a need to impose an interface condition between two subsystems. Based on cyberphysical feasibility and testing capabilities, we have identified that one transfer system will be needed to enforce the thermal coupling between the cyber and physical environments at the contact surface of the structural protective layer and structural system. Therefore, the concept for the thermal transfer system was developed, and its main objective is to effectively apply the thermal boundary conditions throughout the entire surface of the physical structure at the lab. First, however, to implement this thermal coupling with high confidence, we need to understand and identify the dynamics of the control plant and develop effective control strategies. Now, let's dive into our cyberphysical testbed, where we find the three main components that form the thermal transfer system. A chiller, which is a mechanical device that adjusts the temperature of a fluid through a refrigerant cycle, a pipe system to transport the refrigerant fluid from the chiller to the physical subsystem, and a thermal transfer panel, which is a cold plate design involving a flat plate with S-shaped pipe channels circulating fluid on its top surface, allowing it to serve as a heat exchanger between solid surfaces. The current testing and studies for the thermal transfer system are implemented in the pressurized box. To realize the desired temperatures at the box's surface and any other system, we first identified the dynamics of the different components by carrying out open-loop testing for the control plant and measuring the temperature at various locations. From the stage area at the cyberphysical testbed, we sent command or set point temperatures to the chiller and measure its outlet temperature. The chiller was modeled by identifying its cooling characteristics when the two-phase refrigeration cycle is on, with the set point temperature as an input and the outlet fluid temperature as an output. Saturation is implemented to account for the chiller limitations. The refrigerant fluid travels through the pipe system from one location to another. Basic assumptions were made to model the pipe system as a lumped first-order transfer function. A transient lumped capacitance approach assumes all thermal resistance and capacity are in the fluid, which is the heat transfer medium. The model results in a lumped parameter in the unit of time, yielding a first-order transfer function with a denoted time constant. The input for the transfer function is the chiller fluid temperature, and the output is the temperature of the fluid as it circulates on the top of the transfer panel. Additionally, as the fluid travels, an external heat gain was identified and accounted for in the modeling. The most challenging component to model is the thermal transfer panel, as it is a solid plate whose temperature data is limited to the number of sensors. A total of 9 sensors were placed in the thermal transfer panel. From experimental results, a temperature variation can be observed through the panel's surface. Within engineering judgment, it was assumed by the team that the middle temperature served as a good effective assessment measurement of the heat transfer between the solid and fluid components. And a first-order transfer function was identified by using the middle temperature of the panel. Similarly, the modeling accounts for an external heat gain from convection inside the pressure box. From the open-loop experiments, the team confirmed that a controller had to be designed to generate the needed chiller set point temperature to achieve the desired temperature at the interface of the thermal transfer panel and pressurized box. A closed-loop control plant was developed in Simulink using the identified transfer system models and the middle transfer panel temperature signal as control feedback. A combination of feed-forward and PID feedback control was used to develop the controller. PID control is widely used in thermal systems, and feed-forward control is known to help reduce the error of slow processes with high time constants. After computationally implementing the controller and tuning its gains to achieve good performance, the team gathered at the lab and implemented the controller for the thermal transfer system. Due to thermal processes taking a significant amount of time, we will show the accelerated results of the closed-loop experiment. In this demo visualization, the plot will show the set point temperature for the thermal transfer panel sent from our real-time computer. The middle plot will show the temperature signals relating to the chiller, both the command temperature from the controller and the measured outlet fluid temperature. The bottom plot will show the measured mid-panel temperature, which is the feedback signal to our controller, along with the set point signal for comparison. On the right, you will see the measured temperature distribution for the 9 sensors placed in the thermal transfer panel. The tracking error for the controller and the mean panel temperature will also be shown on the screen. For this experiment, the set point temperature is a step function initiating from an ambient temperature of 20 degrees Celsius and dropping to -10 degrees Celsius. As you may see, the command to the chiller reaches the conservative maximum cooling capacity of -65 degrees Celsius to get to the set point temperature as fast as possible. With some time lag, the thermal transfer panel starts to decrease its temperature, most effectively at mid-panel. Some convergence variability may be observed through its surface. At 840 seconds, the mid-panel temperature reached the desired set point temperature, with an overshoot of 15%, something that we weren't able to achieve while running our plant as an open-loop system. The average temperature of the panel after reaching settling time within 5% is very close to the set point temperature of -10 degrees Celsius, considering the uncertainty due to measurements and the conductivity phenomenon. The characterization and identification of our control plant and our systematic approach allowed us to design a baseline controller to attain our control system goals. Soon, further controller requirements will be developed to optimize the performance of future cyberphysical experiments. Thank you for watching.